Hello, you absolute legends. We have a balanced chemical reaction here, and we're going to talk about the predictive power of a balanced chemical reaction. We have a reaction with hydrogen gas, H2, with oxygen gas, O2, reacting to produce water, H2O. And we have it balanced with the equivalence of 2 to 1 of the reactants, and 2 equivalents of water will be produced there in this combination reaction here. Now our question is, or excuse me, let me back up a second. If you had a 2 to 1 ratio in your lab bench, you could easily say, okay, 2 to 1, that matches the balanced chemical reaction. I'm going to say a 2 right there. Let's say on your lab bench you had a 4 to 2. You could predict how much is right here. Like, just using a little bit of mental math right here. We have double the amounts. We're probably going to produce double of this right here. So that's one thing that's helpful with the predictive power of balanced chemical reactions here. But let's consider something like this, where in our reaction on our lab bench, we have 5 H2 molecules, and let's just say 5 O2 molecules. Let's make this number a little different so it comes up to be a little different. Let's make this 3, 5 and 3. How much water could be produced if we had a 5 and a 3 ratio? We can solve this using a graphical, cartoony method, going one at a time here. So we're going to draw some boxes that represent the reaction vessels that you have in your lab. And the first thing we're going to consider is the H2. So this is our before box, and this is our after box. And for the time for right now, let's imagine that we only have 5 H2s in this reaction vessel right here. So H2, 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 H2. And because hydrogen gas is a gas, I have these molecules spread out, and I have them filling the container. So I'm imagining that this box is like on the table, and they're filling the container from top to bottom. These molecules are moving in straight lines, buzzing like bees, until they either bounce off a side of the container or bounce off one another here. How many waters could be produced if I have this many hydrogens? Let me draw some of the afters and kind of cross things out. So H2O, if 1 water is produced, that's going to consume 2 hydrogens. I still have 4 left. So H2O, that's going to consume that one. H2O is going to consume another pair. 1 more water. All right. So that is my prediction for the 5 H2s. If I had 5 hydrogens, this is the most I could produce right here is 5 waters. That is one answer, not necessarily the final answer. Let's consider the other situation, or the other reactant. What if we had 3 O2s? How many waters could be produced? Again, I have these drawn here as gases filling the container. So if an H2O is produced, H2O, whoops, let me draw it out like this. H2O right here. 1 oxygen's consumed or used up. There's the other one. So with this graphical cartoon method, it's helping me keep track of the oxygens that I'm using and the oxygens that are being reacted to produce water here. Now with 3 O2s, 6 waters is possible. Now let's consider for a second here, okay? When we had 5 hydrogens present, 5 waters could be produced. When we had 3 oxygens, 6 waters could be produced. But which is the correct answer, 5 or 6? Let's put them together in the same reaction vessel. The 5 H2s and the 3 O2s, and see which one of these is correct. So we have, I'm going to put down H2, I'm going to put in 5, just randomly splattering them around the container. These were 5, and then 1, 2, 3. So if 1 water is produced, H2O, that would use up 2 hydrogens and 1 oxygen. I'm just randomly crossing them out in here as far just as an accounting to keep my ducks in a row. What if another water was produced? H2O. I still got some more left, so we can make another water, or another water would be made. Another one still. H2O. H2O. I am out of hydrogens. I have an oxygen dangling left over, but I am out of hydrogens. So, what is our answer for the number of waters that could be produced? 5. Of these 2 here, the lowest was the correct answer here. And we can see when we put both of them together in the reaction, we can count very clearly how the hydrogens are consumed to make water, and the oxygens are also consumed to make water. And when the hydrogens exhaust themselves, they become our limiting factor because we run out of those first. And that's what makes us choose the lowest answer of the 3 here. We can see that we have the oxygen in excess. We got a dangling oxygen left over. And even though we have that dangling oxygen left over, we can't make another water because conservation of matter, we need some hydrogens. The lowest answer is the best answer. I hope this helps. Thank you.